All right, this video is for the May 2018, so that is the spring 2018 final exam. So it's another optimization question. So again, we're looking for what am I optimizing, and what is my constraint. If you sneak towards the second part, it says we're minimizing cost. So minimize cost, and then at the beginning of the word problem, it says that we have an area that's 200 square meters, rectangular garden. So my constraint in this case is 2000. And the fact that we have a garden, rectangular garden, I'm going to zoom in a little bit and draw here. Right, so let's set x be the length and y be the width. So in this case, my constraint is 2000 is equal to x times y. So the constraint gives me two things, right? The first thing is that it allows me to eliminate a variable. The second thing is it helps me with the relevant domain. Okay, so now let's look at creating the cost question, right? So let's say C for cost. The cost, one side of this diagram will cost $90 per meter, and then the remaining sides will be 25 per meter. So in this case, it's really up to you which one you decide to be the $90 meter side. I'm going to let this be the 90, and so these sides are going to be 25. All right, so my function, my cost function will be 90y, right? That's my expensive side. 25x, $25y, and then another 25x. So all in all, 90 plus 25 would be 115y plus 50x. And again, you have too many variables because it says you want it to be in terms of just x here. So you go to your constraint equation. Your constraint equation says 2000 is equal to x times y. You divide both sides by x, and then that's what gets plugged in. All right, so now we have a function in terms of one variable. We're ready to now talk about the domain. All right, so remember that the domain in this geometric object has to be bigger than 0, right? If you have 0, then you have no rectangle. And then so now we're looking at the y value. So remember that when x is big, the other variable y is small. So we're going to set 2000 over x equal to 0. And the problem here is if I multiply both sides by x, we're going to get a nonsense equation. Right? If you get a nonsense equation like this, what this means is that your domain is unbounded. Right? There is no number that will that will be an upper bound for x. And if you think about it, you can make this diagram really, really narrow, right, where it's a very large y and a very small x, or you can go exactly the opposite, where it's a really wide x and a really narrow y. So that's why my domain here is all real numbers. Right, so and again, anytime you see a nonsense equation when you deal with the constraint, that means that your domain is unbounded. All right, so now I'm ready to find critical points. I'm going to multiply that 115 right, so this is 230,000 x to the negative 1 plus 50x. Right, take the derivative. Okay, it would be x to the negative 2, which would be a x squared. Whoops, sorry. All right, so this is my derivative. Now I'm going to set this equal to 0, so 0 is equal to negative 230,000 x squared plus 50. I'm going to move this term to the left side. Cross multiply. And divide both sides by 50. 4,600 is equal to x squared. And then we take the square root of both sides. So my critical point is root 4,600. Okay. And so now what I can do is I can take the second derivative. C double prime would be a positive 460,000 x to the negative 3. And so this is the same thing as 460,000 over x cubed. If I plug a positive number into this second derivative, I'm going to get a positive in the numerator and positive in the denominator. So that means that we are concave up. So that means that we have a critical point. It happens to also be a point where the graph is concave. The graph of the function is concave down. Sorry, concave up. Concave up, which would give us a minimum value. All right, so now we're looking for the dimensions. X is my dimension. Let's read 4,600. H would be, if you look back at the beginning, we have this equation, sorry, Y, not H. All right, so my dimensions are root 4,600, and then 2,000 divided by 4,600. And the units here is in meters. I know that because it says right there and right there. Right. So just recapping, the first thing you should do before you do a read through is think about what is my constraint and what am I maximizing or minimizing. So part B tells you what you're minimizing, and then the word problem gives you the constraint. You draw a diagram from there, create your function. You want to isolate the variable you want to get rid of, and then solve for it in the constraint. The constraint, again, also gives you how to get the domain. If you get a nonsense equation in the domain, that means that your domain is unbounded. And once you have function in terms of one variable, you can find critical points. And so you can, in this case, you can use the second derivative test. You can also use the sign chart using the first derivative test. A minimum would be when it decreases and then increases.